All right, we have one last case to go over before we're finished the chapter here, and that is the case where when you're trying to solve a system of equations, the lambda is repeated. So it turns out that there are a couple of sub-cases. One's really simple and straightforward, but takes a little bit of explanation, and one will be a little bit more interesting to get our minds around. So let's see. We are going to be supposing for this that when we're going to find our eigenvalues, when solving a system of equations, linear, homogeneous, etc., suppose that the lambda is repeated n times. Repeated n times when you solve the characteristic equation. We say that in fancy mathy terms, algebraic multiplicity is n. Okay, in this case, we have a few possibilities. And the first is that you're actually able to find n linearly independent eigenvectors. So you're able to find basically enough solutions, enough different eigenvectors to fill up the solution space while finding the solution to that the usual equation that we do when finding eigenvectors. In that case, as you're basically going to get nothing more than the straightforward exponentials that you always would have. And it's kind of interesting because that means that you're going to be having two different parts of your solution that have the same solution form. We talked about this sort of halfway through the course. You're like, well, don't you need your different solutions to be linearly independent of one another? And, well, it turns out that you still can, even if you have the same solution form, as long as the v's are in front of each one of them, are linearly independent to one another. And that can happen in this case. So let's see how that can happen and how they naturally sprout. We're going to deal with this equation right here. So x prime equals 3003x. And I want us to just start by, I don't know, kind of outlining what this equation is really saying. If I reminded you that x prime is equal to, right, it's two dependent variables, and x is equal to just two independent variables, x1 and x2, what this literally says is the following. If I read across the top, I have x1 prime equals 3x1. If I read across the bottom, I get x2 prime equals 3x2. And the two together form our system, but take a closer look. You could have solved either one of those equations way earlier than the semester, like literally at the end of the first week, beginning of the second week of class. We were talking about basic linear equations. x1 prime equals 3x1? Come on, you can do that. And it looks like it's just an exponential at the end of the day. Same thing with x2 prime equals 3x2. So what does that look like in a system form? Well, because none of the other dependent variables occur in, like, the x1 prime equation is only x1 terms. The x2 prime equation is only x2 terms, and a single one of that. This is what's called a decoupled system, because the x1 equation is only x1. The x2 equation is only x2. The two kind of never directly interact with one another. Let's see how this looks when finding eigenvalues. The eigenvalues are, well, we need to find the determinant of a minus I lambda, so that's 3 minus lambda, 0, 0, and 3 minus lambda. I have to set that equal to 0, and that looks really easy. If I do that determinant, it's just 3 minus lambda squared equals 0, which tells us that lambda is equal to 3 repeated twice. So we have that algebraic multiplicity of 2, and I want you to look at what happens when I go and sub this in. So to find eigenvectors, we must solve. And it's the same thing, right? You need to solve a minus I lambda. So a minus, and our lambda is 3, so a minus 3i times v is equal to 0. That's what we need to solve. That's our lambda. And in other words, we need to solve, let's sub in 3 into our a minus I lambda equation right here. And that's going to, so I'm going to write a minus lambda I with lambda equals 3. Oops. Okay, just to make it clear where we're subbing into, because watch what happens. I sub in 3, I get 0, 0. 0, 0, 0, 0. A system of equations that says almost nothing. Think about this. We're basically asking what v1 and v2, we're finding eigenvectors, what v1 and v2 satisfy this very difficult system of equations. 0v1 plus 0v2 equals 0, and 0v1 plus 0v2 equals 0. And it's pretty clear that basically anything goes. You have a two-dimensional solution space here. We have two different degrees of freedom here. We have two free variables to work with. And so we can get two eigenvectors out of this. That as long as they're linearly independent from one another, we get any sorts of combinations of solutions we want. So keep it simple. Just take two free variables, let each one of them have its own sort of, like let v1 equal s, let v2 equal r, and let each one of those be whatever they are, right? That's the simplest way to find those two different eigenvectors. So that's what I'm going to do. I'm going to let v1 equals s and v2 equal r. And either one of these can be anything you want it to be. Okay, any combination of those is going to form a solution vector. So v is equal to, check this out. I'm going to write this as 0, 1, r plus 1, 0, s. Right? Any amount of one component plus any amount of the other component. Right? You can choose the r and the s to be whatever you want them to be, as long as they're not 0, so that we get non-zero solution vectors. But I'll choose them to be 1 to be as simple as possible. So I'll choose r equal to 1 and s, but you should be able to choose them to be whatever you want, as long as the two different solution vectors that you get are linearly independent from one another. And we have that here. So I'm going to let v1, I don't know, I am so inconsistent with whether I use superscripts or subscripts, but v1 will be 0, 1 here, and v2 will be 1, 0. So we get two different vectors here, and those are going to correspond to two different pieces of the solution. Our solution is nothing more than this. C1 times V1, that's 0, 1, e to the lambda, our lambda was 3, so e to the 3t, plus C2, our V2 is 1, 0, e to the 3t. And you might have some concern that the two different pieces of the solution here have the same exponential. How do you get linear independence? But it's exactly because we have the two different eigenvectors that let us span the solution space properly. Take a look, right? The first exponential only belongs to the second coordinate, the second component of that of the solution. The other exponential only has to deal with the first. So we have essentially the C1 and the C2, the arbitrary constants. The bigger or smaller they are determine how much exponential goes with that one component. And essentially what happens is that you get a valid solution here that represents what we thought would be the solution before. Right? Remember at the start that I said you could solve these x1 prime equals 3x1, x2 prime equals 3x2 independently of one another. You should get two different constants in the end of the day, one for each solution. And that's what's true down here, right? Notice, I have exponentials in both coordinates, but because they belong to different arbitrary constants, because they're attached to different arbitrary constants, a proportionality, like one of the pieces doesn't depend on the other. The amount of exponential in the second coordinate here, right, as C1 increases, doesn't increase the amount in the top coordinate, and so on, the x1 coordinate. If I wrote this down coordinate-wise, like just one at a time, we could write x1 equals, well, it looks like we have here c2 e to the 3t, and x2 equals c1 e to the 3t. We get two different solutions, each one with its own constant. And yeah, that's kind of how it goes. It's actually a very simple case. You just kind of have to know what to expect in order to tackle it properly. So it begs the question, what happens when you don't have that? What happens when you don't find multiple eigenvectors? And that is certainly possible as well. So it can also happen that fewer than n eigenvectors are found. It's problematic, but only because we don't really know what kinds of solutions to search for a minute. But we're going to deal with the 2x2 case here. And again, there's some more interesting derivations. There's a lot more to the story. I know I've been saying that a lot lately. But there's a lot more in the background here that will be covered in differential equations too. Here, for now, we'll be just interested in, what do the solutions look like in this case, and why can we believe that those are the solutions? So that's what we're going to work on right now. Okay? If you find only one eigenvector, but you have a repeated eigenvalue, then you're going to get a single solution out of it, but you need more. Okay? There's more to the whole solution. So the first solution is exactly what you'd expect. x1 equals v e to the lambda t. So the same thing. You take the vector that you found, you slap it in front of an exponential, and it's the exponential associated with the eigenvalue. Then just like in chapter 5, if you remember, we had repeated roots for single equations. And in that case, you have exponentials, and then because you need a second linearly independent solution, it turns out that what you need is a second solution that's in the form of t times the same exponential, and you add that to the picture. And here it's very much the same thing. This is the case that's parallel to that from chapter 5, the repeated roots there. But it turns out that the second case has a little bit more to it, okay? We have here x2 equals v t e to the lambda it. So the same vector, this is our eigenvector. The lambda is our eigenvalue as usual, and p is some other vector. Not sure what that is, but we're going to do a bit of a derivation to see if we can figure out what that p thing should be. So we're going to take this solution form. This is what we need, but we're going to sub it into the differential equation so we can see what the different pieces look like. So our equation was x prime equals ax. That means I need a derivative of this thing. So let's carefully take a derivative. And it looks like if I take the derivative, I'm going to get here, okay, v out front. The derivative of t e to the lambda t is the derivative of the first times the second plus the first, there's a t right there, times the derivative of the second, lambda I comes down, e to the lambda it. Okay, I still need the derivative of the second part, this right here, and that's going to be lambda I times whatever the p is, e to the lambda it. On the right, we have a times x, and so we're going to sub in, just rewrite what we have right here. So that's vt e to the lambda it plus p e to the lambda it, just like that. Okay, couple things we want to observe here. First of all, we have exponentials common to every single term in this whole thing. Exponentials are non-zero. Guess what we're going to do? We're going to divide everything by e to the lambda it and just get rid of them. So this is gone, this is gone. All 5 of them are gone. That will simplify matters quite nicely. The next thing we're going to do is, let's bring all the t terms. Let's bring things to different sides and see what happens here. So, okay, I'm going to have here a v times lambda it. So I'm going to write lambda I v t, perhaps. Lambda I and t are scalars, so no problem with the order or anything like that. But I'm going to take the t term from this side and bring that over as well. So I think we get here minus a v t, just like that. All right, I'm going to sweep the other terms to the right-hand side, and we'll see what happens. So I think we have an AP. Some of you will have taken AP calculus before this, not the same AP. All right, and yeah, see, I made a little quip and then I lost my way. I was like, should I make fun of AP Calc students right now? And I was like, maybe not. I don't know. Seems like it's poor form. But oftentimes those students will come in and think that they know like absolutely everything on the whole planet. And, you know, sometimes they need just a little bit of a talking to put them in their place. But generally speaking, I've talked to some really brilliant students as well, and mostly they're just proud to show off some of the things they know. So I won't make fun too hard. But anyway, let's keep going here. All right, so I need to figure out what to do with this thing, and it seems like it would make some sense to factor out the t on the left. So lambda I v minus av, I'm going to factor out t here. And at the same time, maybe I'll write this as, maybe I'll bring over the p and factor that out as well. So a minus I lambda I. Factoring out the p right there. I still have this minus v over here. Okay, there's some funky stuff I can do. First of all, you might stare at this for a little bit and then notice something quite interesting. Because v is an eigenvector and lambda is an eigenvalue, that means that this term right here, this one that I put the green brace under, is going to equal 0. And that's because AV equals lambda IV by the definition of an eigenvector. Okay, wait, that's cool. I should be a little bit careful, right? This is actually a vector, so this is a vector of zeros. The v and the p are vectors. But then if it's 0, and I have 0 times t, that's just going to end up being a 0. And I can bring over that v now, and I get here v equals a minus I times lambda I p, just like this. And that is what we get to right here. But let's think about what this is. Okay, v was an eigenvector. V satisfies, so note, v satisfies a minus lambda I v equals 0. So what we're saying here is that p is some other vector where I stick it in v's place and v goes in the 0's place. A minus lambda I p is equal to v. So here's how it works. You can actually solve for the p once you've got the v by solving one more system. And we'll see in an example exactly what that's going to look like, but it's not too bad. P is called a generalized eigenvector. And it exists as part of this solution, as a second sort of linearly independent piece that hits an exponential, while the v is in front of the t e to the t term. If we need one generalized eigenvector, so that is we find a repeated root of multiplicity 2, but we only find one regular eigenvector v, we obtain one solution that's what we usually would get, like this, and a second solution that is of the form that we searched for. So you stick v now in front of a t e to the lambda it term, and then add in this new p thing. Okay? So that is how this is going to work. I kind of brought you through to see what the different objects at least would look like, given that this is the form of the solution. But there's a lot more, as I said, to the story in the background, and there are more details to come next semester. So, things do get more complicated if you get like repeated eigenvalues in higher dimensions. So you could be like short either 1 or 2 eigenvectors in a 3x3 case. And in that you get like, you know, some sort of a t squared e to the t term, but it's in combination with other things and so on. I've had some extension questions in the past that have explored this a little bit simply by considering a system of equations and getting students to write out some things and figuring it out. And it's been kind of cool to explore some of that stuff. But for now, we'll concentrate on basics and deal with this example down here to round out the chapter. So, x prime equals 2032x. We'll start by finding eigenvalues. and the eigenvalues satisfy the determinant of 2 minus lambda, 0, 3, 2 minus lambda equals 0. And of course, when you figure this out, the determinant is simply going to be 2 minus lambda squared equals 0, which means that lambda equals 2 twice. So there is that repeated root of the characteristic equation, and we are going to go and find eigenvectors now. So eigenvectors satisfy. And so we're going to go through, we're going to plug in that 2. I'm not going to write down the a minus, we know what it is. I'm going to plug in 2 into this matrix, and we get 0, 0, 3, 0 with a 0, 0. And you can see that unlike last time, we don't just have zeros everywhere. We have a little bit of structure here. So let's look at the equations. The only equation that really has any substance here is the second one, which says 3v1 is 0. Okay? So again, don't just leap to saying, oh, I think I want to choose whatever component I want to be free here. This is a system of equations that describes a relationship between the variables. And the second equation tells me that 3v1 is 0. And that means that v1 is equal to 0. It can't be anything. So think about it before you write it down, okay? So, from row 2, 3v1 equals 0, and that forces v1 to be 0. But that means that the free variable has to be v2. So v2 is equal to s, where s is some real number. And we get an eigenvector. We get v1. I'm just going to write v because we're only going to get one of these v's. V equals, and I'm going to write it as 0, 1. Choosing s to be 1. Okay. So we only got 1, not like the last one. We only got 1 eigenvector. So, yeah, we are going to have to find a generalized eigenvector here. And that means we have to solve a different system. So to find a generalized eigenvector, it's not going to be that hard, but it's a little bit interesting, and it'll feel a bit weird maybe. We're going to solve a minus I lambda times p equals v. So that's what we're going to want. And so that means I'm going to do the same matrix, the same, like, you know, I'm going to take this exact same matrix here. I'm still going to plug in 2. That's still going to go in the same place. But the thing I'm going to put on the right is not 0, 0. It's going to be 0, 1. It's going to be the old vector that I had. So rather than the 0 vector on the right-hand side, I need something else over there. So we need to solve this equation right here. And it's going to be 0, 0, 3, 0. And on the right, I'm going to put the old eigenvector. And our solution to this is going to be our p vector. So let's read what this says. From row 2, 3, well, I guess I'll call it p1. 3p1 equals 1. And that's a little bit interesting, because what this does is it forces p1 to be strictly 1/3. There's no degree of freedom there. P1 has to specifically be 1/3 in order to have the structure that we have had before. P2 looks like there's no restrictions on it whatsoever. There's no other information in this system of equations. P2 doesn't even appear in either one of the equations that are in the system. So it looks like P2 is going to be equal to something. I'll choose another s with s belonging to the real numbers. And if we write down a vector p, p is going to equal, well, it looks like it's going to be 1/3 and s. And we have to choose s to be whatever we want it to be. And it literally can be anything you want it to be. That might seem a little bit interesting. And in fact, I often do an exercise. I sometimes do a little bit of work in lab and stuff like that to show that, in fact, S can be anything. So, tune into the last lab if you're interested in seeing a little bit more about this. But trust me for now, if you're solving an initial value problem and so on, and applying an initial condition, you can show that no matter what you choose that P to be, if you have a little bit of flexibility on what you choose the S to be, you will still get to an answer that works out to be the same thing, no matter what S you choose. So we can choose S to be anything, and I'm going to choose S to be 0 here. Here's why. Usually we say that we can't choose S to be 0 because it would make a 0 vector, but here it doesn't. If I choose S to be 0, I get 1/3 0, which is not a 0 vector. So it's fine. Plus, from the discussions before, I just need P to be something linearly independent to the V, again, to give me a different combination of exponentials, the same exponential across both terms. And 1/3 S is always going to do the trick. So I'm going to choose S to be 0. So choosing S equals 0, we get P equals 1/3 and 0, which is linearly independent to the V we found, which was 0, 1. So let's write down a solution. And we'll look at what this looks like. Our solution is, I forget, were we X or Y here? X. Our solution is X equals, let's write down the first. So X is equal to C1, V1, and V1 was 0, 1. E to the lambda, and the lambda was 2, so e to the 2t. This is the first part of our solution. The second solution is bigger, c2 times. And now, what do I need? I need the new thing times e to the 2t. So c2 is going to be hit by 1/3, 0, e to the 2t, whoops, e to the 2t, just like that, and then plus the old thing, the old eigenvector, the original, the OG v, 0, 1, this time t e to the 2t. I want you to think about it this way. The things that are hitting, like the same eigenvector, 0, 1, this couldn't be another e to the 2t because that already appears in the equation. So thinking of, I need something a bit new for that, the thing hitting 0 to 1 had better be new, or 0, 1 had better be new. It has to be the t e to the 2t term. So that's why that's there. Meanwhile, the new linearly independent eigenvector, 1/3, 0, has to be the thing that's hitting the e to the 2t, right? To make sure that I have a different combination. These are linearly independent. So I am still adding some new things, okay? And if this second component, right, that was what we had chosen for S. If you chose it to be a bazillion, that's not actually a number, so if you had chosen it to be 750 million, that's totally cool. And what will happen is when you go to find initial conditions to an initial value problem, your value of C2 will be different than mine will be to make sure that the solution works out to be the same thing. So you actually have a ton of flexibility there. So yeah, just going through, this was our V, this was our V, this was our P, and you can see the different kinds of solution forms that appear. That's what our final answer looks like. So this is such a rich topic. This is a huge area with so many more details. Graphing some of these solutions is incredible. It's very, very interesting, and it's a very rich and deep area of mathematics. As I said, there's almost a whole course devoted for it. And if you're liking some of this stuff, if you want to learn a little bit more, I urge you to take that second differential equations course. Otherwise, I strongly advise you to learn those 3 cases: real, repeated, and complex eigenvalues. Learn the solution forms and be ready for any of them. A lot of students fall into the trap of not practicing this as much and then thinking everything looks like the real solutions form. And it doesn't. You have these different kinds of solutions that pop up. So be prepared for it. Expect it, and you'll be fine. Okay? Let me know if you need any help. As always, office hours are open, my email's open, and I hope you will come to see me. For now, we have one last chapter and a couple more videos to go, and we'll be calling it the end of the course. So I hope you've enjoyed the ride so far. One last chapter to go. We're going to get into it in the next video. So join me then. Ciao for now, and I am signing off. Take care of yourselves.